Okay, so this problem is one of the more challenging problems. I suggest not trying to do this problem until you've kind of mastered this section and then come and see if you can work through this problem. It's difficult mainly because of taking the derivative and then that second derivative. You'll notice it's a quotient rule, but on top of a quotient rule, you've got a product rule up there, so it might be helpful to multiply that out. But it just gets kind of complicated the more derivatives you take and finding the zeros and solutions. So, I just caution you coming into this. If you can't get it the first time, don't get discouraged. This is a more challenging problem. Okay, so let's just start with this like we start with every problem. First thing I want to do is I want to for curve sketching, I want to find the domain of the function. So the first thing I do with a rational is I set the denominator equal to 0 and try to solve for x. So this is something, multiply to 4 and add to 2. Not really anything that I can do that I can think of off the top of my head. 4 times 1 adds to 5, and then 2 times 2 adds to 4. So that doesn't really work. So I'm going to have to use a quadratic formula here. Negative b plus or minus square root of b squared minus 4ac. So that's where the 1 and the 4 come from. And then all divided by 2a. And the a here is 1, the b there is 2, and the c there is 4. Okay, if you work through this, you're going to get in this denominator, or inside the radical, 4 minus 16, which is square root of negative 12. Well, if you know anything about square roots of a negative, you know that you can't have a real number here. You got an imaginary number. So this is complex. So that tells me that there's no real solution. There's no real number I can plug in the denominator that's going to make this 0. Therefore, if there's nothing I can plug in to make it 0, then all real numbers is my domain for the function. Okay, so a little bit different seeing a rational that doesn't have a vertical asymptote, but it is definitely possible, and this is an example. Now, like I said, to kind of limit the product rules and the quotient rules and all that jazz, what we're going to do is I'm going to multiply out the top, and I get 5x squared minus 5x minus 10, okay? If you distribute all that out. And so what I'm going to do is I'm just going to apply the quotient rule here. So low d high. So low d high, the derivative of the top, that's 10x minus 5. And then minus high, which is that thing right there, d low. The derivative of the denominator, that's just 2x plus 2. All over low, so I square it. Now I need to clean up the top. Okay, so I'm going to let you multiply out, distribute. Look, you're going to have to distribute this to each term here, and then distribute that to each term there, and do the same thing for that second piece, and then collect like terms. It's a lot of work, okay? But you can definitely do it. It's more of an algebra exercise than it is a calculus exercise here. You're just distributing and collecting like terms there. Denominator stays the same. In the numerator, you should get 15x squared plus 60x. All right, like I said, a lot of algebra, but you can do it. It's definitely doable. And I'm going to factor a 15x out of each term, and that's going to leave me x plus 4. Now, for a fraction to be equal to 0, that means the numerator has to be equal to 0. Well, the only way the numerator is equal to 0 is if x equals 0 or x equals negative 4. Okay, so those are my solutions when I set the numerator equal to 0. What about setting the denominator equal to 0? Well, what do you notice about that denominator and this denominator here? They're all the same, right? And when we set that equal to 0, what did we find? We said that there was no real solution. So there's no way to find a derivative that does not exist. We're stuck with just this right here, x equals 0 and x equals negative 4. Now, this work right here is the work of getting the second derivative. So this is the derivative of that function right there, if I take the derivative d dx, then I get this big nasty thing, and I work through some algebra, and you can see that's kind of a headache. So I'm just going to simplify it for you. This is, voila, magic. All of a sudden, you went from the first derivative to the second derivative. Okay, so kind of cheating a little bit. If you want to look through these steps, be my guest. I'll zoom in real quick so you can kind of check yourself, make sure you can get it. Okay, that should be long enough to get your screenshot. And so how do we know when the second derivative is set equal to 0, I set the numerator equal to 0. Negative 30 is never going to be 0, but if I set this equal to 0, I'm going to find some roots, okay? I use a calculator here, so just type in your calculator x cubed plus 6x squared minus 8. Find the zeros. These are the 3 zeros that are listed. Negative 5.759, blah, 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 all 3 of those there. You know, you round to whatever the problem tells you to round to. Here, it didn't say what to round it to, so you know 3 is fine, 2 is fine, whatever. It's kind of hard to count off for rounding if I don't specify what to round to. So you make that judgment call. Just don't be like, oh, well, I'm just going to round to negative 6. I want a minimum of 1 decimal point anytime you have to round. 1 decimal point is like the minimum, okay? All right, so once again, we have the same denominator going on here that we've had in all the other ones, and we know that that can't equal 0, so there's no way that the second derivative doesn't exist anywhere, but the numerator set equal to 0 produces these possible inflection points. So we've got 2 possible relative max and mins, and we got 3 possible inflection points. Now, what I'm going to do with those values, once I find the vertical and horizontal asymptotes, is I'm going to connect the dots. So let's do vertical asymptotes. Well, what do we know? The denominator cannot equal 0. So what does that tell me? There's nowhere where it doesn't exist. Thus, we have no vertical asymptotes. Pretty easy, right? So you knew as soon as you wrote down negative infinity to positive infinity, you think about a polynomial that doesn't have any vertical asymptotes on it. Okay? Horizontal asymptotes I find by taking the limit. The limit as x goes to infinity. So limits at infinity. I look at the highest degree term. It looks like they agree. They're both x squared. So I divide the coefficients. 5 divided by 1. It's an understood 1 there. And so that gets me 5. Now, plus or minus infinity doesn't matter here. Why? Because there's an x squared term. So whenever I square a negative number, it still turns out being positive. Okay? So that one kind of worked out for us. It's positive 5 for both of them. So y equals 5 is my horizontal asymptote. So now I've got my horizontal and vertical asymptote. So no vertical asymptotes, and we have 1 horizontal asymptote. I want to use my critical values I found for the first derivative to write out my subintervals. And so I've got, looks like 3 subintervals for this first one. So here and here is where the derivative was 0. So I want to pick points in between. So I just pick -5, -2, and 1. If I plug that into the derivative here, so here's my derivative. If I plug in a -5, well, I see that that becomes negative. This becomes negative. So negative and a negative make a positive up top. And then in the denominator, when I square it, that's going to be positive. So this number here is going to be positive. And so that means that we are increasing on that interval. Now -2, a little bit different. -2 here makes that a negative. Here is a positive. So a negative and a positive make a negative. Negative in the numerator, positive in the denominator makes a negative. So this is negative, decreasing here. So increasing, decreasing. Ooh, that looks promising for a maximum. And then this last one, I'm going to plug in 1. If I plug in 1, I get a positive, a positive, a positive makes a positive. So I'm increasing. So increasing, increasing, and then decreasing on that interval. Okay, now I'm going to take these critical values for my possible inflection points, and I'm going to plug them in. Values that are in the subintervals. So these are my subinterval values I'm going to plug in. Again, no magic to pick a -6 or 10 or 0 or -2. I just need numbers in between the critical values that are potential points of inflection from the second derivative, right? So this came from the second derivative. Now, once I evaluate -6 in here to my second derivative, I plug a -6 into this nasty thing right here. This is going to give me a positive value, okay? If I plug a -2 into this second derivative here, that's going to give me a negative value, concave down with a frown, right? If I plug a 0 in, looks like a negative times a negative is a positive, and then that's going to be a positive, so that's probably going to be positive, yep. And if I plug a 10 in here, then that's going to give me a negative value there, okay? So now we see that we've got concave up, and then concave down, and it looks as though since f is defined for all real numbers here, then every one of these are going to be inflection points since we're swapping between concave up and concave down, and each of these are going to be either relative max or relative mins. So we've got lots of relative max, relative mins. I've got all those values. Now I just need to find the points and the x-intercepts. So x-intercept, I set y equal to 0. And to do this, the only time a fraction equals 0 is whenever the numerator equals 0. We don't even care about the denominator because that can't be 0, right? So we set that equal to 0. You can factor, and you're going to get x equal 2, x equal -1. For the y-intercept, I set x equal to 0. And if I set x equal to 0, then everywhere I see an x, I'm going to plug in 0. And so what do I have left? All I have left is -10/4. So that's -10/4 for my y-intercept. So that's -5/2. Okay? So those are my points for intercepts. I've got points of inflection here. These are just the x values. We're going to have to come back and find the points. So there's 5 x values. I need to find f values, y values that are associated with it. And I've got 3 intercept values here. So several points that I'm going to need to connect the dots on. First thing I'm doing here is I'm going to show you all of the different points. So 1, 2, 3, 4, 5, 6, 7 points here. And when I do this, I've got the -5.7 point there. I've got the -4 maximum here. Okay. And then here looks like it's another change of inflection, the 1.3 point. And then the intercept, y-intercept for that one. The x-intercept for this one, and the y-intercept for that one. And then I have another change in concavity point of inflection. Point of inflection. And then here another x-intercept, and we go on from there. So I'm going to zoom in for you here. So this was a concavity change. This was a relative max. Concavity change, x-intercept, relative min, concavity change, and then x-intercept here. Okay, so those are all my points there. You'll need to find the y values. And then on the second part here, see this first graph, all it did was tell me I'm increasing, decreasing, increasing, right? There was no concavity here. We use the second derivative to tell us how we're concave. So I'm going to use my highlighter here. So this part up to here, up to this 5.7 part, we're concave up. And so we are concave up right there, okay? Then here we are concave down between 5.7 and 1.3. So 5.7 and 1.3, this is concave down like a frown, okay? Here we are concave up like a cup. So negative 1.3 to 1.06. So we're concave up to here. And then the last one, we are concave down like a frown. So even though we're increasing here, we are concave down at that point, okay? So keeping in line with what we've done in the past, so we're increasing, we're plus, and then we hit the max, so now we're decreasing, negative, and then we hit the relative min. This kind of looks like an absolute min, right? And then we're increasing, plus, okay? And now on the top side, we do our concavity. And so our concave up here, we're positive. And then all of a sudden we switch to be concave down, negative. This tells me you know what you're talking about. And then we're concave up, positive. And then we switch to be concave down, negative. Remember, I like for you to put your concavity plus minuses on the top side of the graph. And I like for you to put your increasing versus decreasing versus increasing plus minus signs on the bottom side of the graph. That way it tells me, you know, this is on this region of the graph we're concave up, concave down. Because sometimes it's difficult to see the concavity of a picture. Like you really can't tell the concavity on that part. Okay, so very important that you write that out. That way we can, you know, I can know for sure that you know what you're talking about. Like I said, this is a challenging problem. One of the harder ones, so if you don't get it right off the bat, that's okay. Really, probably the issue is going to arise in calculating the derivative, but if you can get that down and then rely on technology to get your x-intercepts, then that's really going to help you out. And to get these values, the points, the y values, you literally take those x values and plug it into this nasty part. I didn't even show that part there just because it's a little messy, but you know it's something that you can do. It's just algebra intensive, takes a lot of time, but you can push through.